Hopefully you can hear me. Thank you so much. It's 4 o'clock. It's been a long day for you. So thanks for taking the time out to be with me here today and be with us in Griffith College, just to maybe plug a few gaps or a few holes in your memory of all the topics you've learned on maths so far. Hopefully the first 3 sessions have helped you fill a few gaps and to remind you of all the stuff you knew and maybe fill in a gap or two where you weren't clear fully before. But if anything else, I hope they've helped you sort of take on board that really it wasn't all that more difficult than all the stuff you already know. And filling in those gaps maybe helped you join up a few bits. Like I said about Hansel and Gretel, you fill in the white stones and you find your way back. When the stones are taken away, it's pretty difficult. But if they're just put back, it's a lot easier. So we've one topic left to do today. It's complex numbers. It's a really, really interesting, lovely topic. And I want to share that with you. But there's other topics after this session as well. So always feel free to use maths.griffith.ie. Come back to that. That resource will be there until after your leaving cert examinations. Má tá si bh na scrúdathe Australia, tá áisina ar fáil Australia comá. Not the full course Australia, but some, and hopefully they'll help you as well. And for those taking higher as well, we've got the sessions there as well. So we'll be going live with that on Sunday as well. So that's our plan, but thank you for your time today. So it's now time to start. I'd like to thank my team as well. John has been great. He's the technical person in IT. John and Rob have been curating all the comments that have come in. So thank you to both. Thanks for all your questions and all your comments. We've been able to take those on board and to answer those as they came in. Questions like how often does a question come up, like that question about acceleration? It doesn't really matter as long it can come up. That's the point. And if you're ready for it, it's just fairly straightforward. Differentiate once, differentiate again, and you get the speed and the acceleration and you're done. It's not going to change. So knowing it is helpful. So I'd like to thank Sinead as well. Sinead, the school's liaison officer, Sinead O'Callaghan. So if you have any questions, comments, queries, anything you want to say or find out, schools@griffith.ie, just give Sinead a buzz and that will come back directly to us then in that. So I won't sign off yet because we have another interesting topic to do, but I just wanted to say thank you, and particularly thank you for being with me at 4 o'clock after normal school time for an hour and a half. We will be finished though on time. So complex numbers, here we go. Just on complex numbers, I just want to put it out there as something that's true, is that I don't believe that there is any person viewing today as a leaving certificate student who has not used complex numbers or had the benefit of complex numbers hundreds of times last week and this week, and probably hundreds of times today as well. And we'll certainly have it before the day is over. I'll explain how often they're used. They're used in everyday life, and our life would be so different without complex numbers. So I'll just explain what that is and how common and ordinary they are. But let's start with complex numbers. So rightly. As I said, if you're new to this, we have the complex numbers written as various sections. So this section here is just a title page. It's just got a rectangular box. So it's the start of a video. So if you want to just understand this little bit or another little bit, it'll help you locate the precise video you want to watch, because you know most things. You're just trying to fill a few gaps in preparation for the Leaving Cert later this year. So we're going to start with some introduction and some terminology or termiot. Complex number is a number that has 2 parts. For example, Z is 5 plus 12i. So it's 2 parts to it. It's got a first part, a real part, and a second part that has a real coefficient and then an imaginary number afterwards. So 5 plus 12i. The I part is the imaginary bit, the 12 is the real bit, and the I is defined as the square root of -1. So it's an imaginary number. I squared is -1. So it seems like a bit arbitrary that we'd have this, but they'll turn out to be really, really ever present, really. The general form of a complex number is Z is equal to A plus BI. And the full set, the complex number set, is defined as the full set, that's the curly brackets, a plus bi, any two numbers made up of a plus bi, where a and b are real and I is the square root of -1. So that's the definition of a complex number. You won't be asked that, but you'll understand where they're coming from. Complex numbers can be drawn on very much like the XY graph paper that we're used to. Here we've got just the top right-hand corner of it, and we're saying that 7 out and 1 up, or 12 out and 5 up, that's really our notes there in that. So that's 12 out and 5 up, so 12 real and 5i, 3 out and 4 up, 2 out and 8 up. So that's it's called the Argand diagram. It's a 2 by 2. We're used to X and Y, but in this case it's called real and imaginary. Réadúil agus Samhailteach. So they're the two axes there on that, real and imaginary. And we just draw graphs on them there. But it does the full lot. It's the full X, Y there. So you've got positives and negatives above and below. So this is 2 plus 2i, 4 minus i, -1 minus i, and say -2, 5i. So it can be any single quadrant. Now, there's a sentence here that's a little bit nearly philosophical, and it says each complex number is fully identified by two coefficients. If two complex numbers are equal, their separate real and imaginary coefficients are also equal. Let's imagine for a moment that complex numbers are no more difficult than, say, oranges and apples. So 2 oranges, 2 apples, 4 oranges, 2 apples, 4 oranges minus an apple. You owe somebody an apple, and 3 oranges and 4 apples. Okay, that's what they are, oranges and apples. Okay, this might be oranges and this could be apples. All this sentence is saying is that if two numbers are the same, if John has 3 apples and 4 oranges, the only way somebody can have the same is they must have 3 apples and 4 oranges. They can't make it up with more amount of oranges or more apples. They've got to have the same in both. We'll see how that's useful in a minute. That's all. But to be on this point 4, 2, you have to have 4 apples and 2 oranges, or 4 plus 2i. There's no way of getting there. You can't have 5 and a little bit less or something else. It must be 4 and 2. That's it. Argand diagrams can also be drawn in some sort of lines or distances in this way as well. Different representations, sometimes called polar. So here we get 7 plus I, or 12 and 5i. But it's to get to 12 plus 5i, you can imagine maybe walking from 0, 0, or 0 plus 0i now, all the way out this way. So that would be the length of it. Or that would be the length of a complex number, or the modulus of a complex number, whereas the coefficients will be 12, 5i, 12 plus 5i. The length would be, well, we'd have to figure out how the length would be. And we'll do that in a minute. The good thing about the real and the imaginary is they're seen to be at 90 degrees to each other, exactly like before. So this distance 12 plus 5 will be 12 this way, 5 this way. Because it's a right angle triangle, 3 and tons run illoch, Pythagoras' theorem applies. So 12 squared plus 5 squared would be this squared, 13 squared, and that length will be actually 13. So the modulus, or the length, or the darabhluk, or the distance from here to here would be 13. And that's seen as the length of the complex number. But we'll deal with that in a moment. So basically, for the general complex number, it's written as this, like 2 parts. It's like apples and oranges, you know, anything at all. Okay. The modulus, also called the absolute value of a complex number, represents its distance. And that's put around brackets here. Now, it's really important. The trouble sometimes with maths is that it can sort of put people off a bit, or can be a bit intimidating. But think of all the numbers you've already learned before. You've learned the numbers 0 to 9. You've learned the pluses and the minuses. You've learned all the alphabet to Z, and there were 26 of them. You've learned the capitals as well. Then you learned the apostrophes, the colons, the semicolons, and all of that, and the exclamation marks. So maths is just the same. It's adding a few more. We've learned the x squared, the square roots, etc. So in complex numbers, we're adding a few more symbols. The first symbol is this bar thing. The modulus, the length of the line. So the length of the line a plus bi. And the value of the modulus is given by a squared plus b squared. I wonder where that came from. A squared plus b squared. Well, it really shouldn't surprise us in a way, because if we look at this length, we took this squared plus this squared to get this squared. So if this was z and the bar of it, the bar would be the 12 squared plus the 5 squared all square rooted, because squaring it would be the same. So that's the way that would work. So the modulus is given by a squared plus b squared. Note that it's not minus b squared, even though you might think it's I squared, but b is a distance. B is not a minus value. B is a distance. So the length in moving from here to here, even though it's 5i, it's 5 meters or 5 kilometers or whatever that unit is. So it's a squared plus b squared, all that square rooted. So that's the modulus of the length. So here's an exam question, and they come up just like this, as straightforward as this. Calculate the modulus or absolute value of the complex number 3 plus I. So the first thing you do is they might show it with bars around it. And then you say, well, the average or the general one is a plus bi. So a is 3 and b is 1. So that's 3 plus 1i really. So a is 3, b is 1. So 3 squared plus 1 squared is 3 is 9 plus 1 is 10, the square root. So the distance is 10. So the modulus or absolute value represents the distance of the complex number from the origin, and its value is always positive. So here we go. 3 plus I on the Argand diagram looks exactly the same as the xy, but it's called real and imaginary axis. This is 3 and that's 1. So that's 3 squared plus 1 squared is 10, or 3, 1, and the square root of 10. So that length, the modulus of this particular distance, is 3 plus I. The absolute value of that is the square root of 10. Distance is always a positive value. You can't be minus somewhere, minus length. You can be in a different direction, all right, but you can't be minus 3 kilometers. You can be 3 kilometers west or north or south or whatever, but it's still 3 kilometers. It's not minus 3 kilometers. So that's where that comes from. So that's the modulus representation. So here we are on the Argand diagram, 7 plus I, 12 plus 5i. And a question is asked, is this number here, Z1, bigger than this one, Z2? And really, is the length of it bigger? Is the length of this bigger than the length of that? And the way that comes down to is it further from 0 plus 0i? So is this point here further from this point here? And this point here is further away. So how do you do that? Well, you can calculate the actual length of that, and you can say 12 squared plus 5 squared is, and that comes out to be 13 when you do the sums. I think 12 squared is 144 plus 25, and that's 13. 7 plus 1 is going to be, it's not going to be as big. 7 squared plus 1 squared, that's 7 is 49 plus 1 square root of 50. And the square root of 50 is about 7, whereas that's 13. So that's bigger. And that's all you'd have to do in a typical question. So that's the first part of complex numbers done. Can you calculate the length of something, a modulus? And that's generally part one of, one of the questions, question 2 or question 6 in the last 5 or 6 years. We're now going to turn to the next topic, the addition, subtraction, and multiplication of complex numbers. Now, I know complex numbers have this imaginary part, but really it's no different than counting apples and oranges or anything else you'd want to buy, chocolate bars and packets of crisps or whatever, just 2 different things together, that's all. So addition, subtraction, and multiplication. So how do we do that? Well, what we're doing there is that we're asked to add u, which is a complex number, 1 plus 3i, to v, which is 4 plus 2i, find u plus v. Now it looks complicated, but imagine if you said, well, John has 1 apple and 3 oranges, and Mary has 4 apples and 2 oranges. So 1 apple, 3 oranges, 4 apples, 2 oranges. I think you could work out what the totals were and keep all the apples together and all the oranges together. It's really straightforward in that sense. So we keep all the bits that don't have the I together and then those that do have the I together. So that's just the addition. So expanding the expression, we say u plus v is 1 plus 3i, I'm just copying it down, plus 4 plus 2i. But I'm now going to break it into the real parts. Let's call those the apples, the 1s and the 4s. And the imaginary parts here, I'm going to show those differently and say that's the I part there. Okay? And maybe use a different color for them or something like that. Okay? So the real parts are the 1 and the 4 there. The imaginary parts are the 3 and the 2. So the 1 and the 4 give me 5, and the 3i and the 2i give me 5i. I could have added them this way, one under each other. 1 and 4, 5, 3 and 2i, 5i. Could have done them that way. And that's how it's done. That's the addition. I might have chosen to represent that on the Argegáin diagram, and that's 1 plus 3i, 1 out and 3 up. V is 4 out and 2 up. So what's the total? Well, 1 out and 4 out would be 5 out. 3 up and 2 up would be 5 up. So effectively, that's how that works. If I went out and up, and then followed by the 4 out and the 2 up, I'd get the same. Or if I went out to 4 out here, and then 1 plus 3, I'd end up in the same place. Doesn't matter which way I go first. So if you imagine this were east and this was north, it would work. If this was X and Y, it would work. But it's real and it's imaginary. That's all. Apples and oranges. Addition is commutative. What they're saying there is that it doesn't matter which order you do them in. U plus V brings you there. V plus U brings you there. So it doesn't matter which apples you count first and which oranges you count first. You get the same amount when you put them all together in 2 different piles. So that's addition. We now look at Jalu, subtraction. And we're saying Z1 is 5 plus 5i and Z2 is 1 plus 3i. Find Z1 minus Z2. So if, Brian has 5 apples and 5 oranges and somebody wants to borrow or eat one of the apples and 3 of the oranges, how many would be left? It's as straightforward as that, really. So what's Z1 minus Z2? Well, again, 5 plus 5i minus 1 plus 3i. I'm just taking this from this, nothing different. Multiplying the minus in, I get 5 plus 5i minus 1 minus 3i. And again, I'm going to link the apples together, the oranges together. So the real bits here, the 5 and the 1, and the 5i and the minus 3i. So I get 5 minus 1 for the reals, and 5i minus 3i for the imaginaries. So then I get 5 minus 1 is 4, and 5i minus 3i is 2i. Again, I could have done it this way, lining it up and sorting that out, and I get the same. If I wanted to do it visually, I could say I'm over here. I've got 5 and 5i, or 5 apples, 5 oranges, and I'm going to subtract 1 and 3. So back 1 and down 3, or I'm going to subtract 4 and down 2, and then subtract the rest. So that's how I would do it. So I can minus twice to get back, minus twice to get back, or minus 1 to get to here, or minus the other to get to there. So that's just how it's represented. Now, the next bit is strange in that it's more sophisticated than apples and oranges. Here we're actually multiplying I by I and things like that. So this is the first step away from just apples and oranges. We're talking about the multiplication of numbers that have 2 parts, this part and that part. So how does that work? Well, the Americans have this system called FOIL, when they multiply 2 things by the other. They start with the first one in both groups, then the outside one from both groups, then the inside one, and then the last one. So that gives them the 4 of them. So let's see how that works. So 1 times 3, so they get 1 times 3. 1 times 3 is 3. That's the first. Then the outside 1 times I is I. Then the inside one is I times 3. And then I times I is I squared. Sorry, that's I times 3, not I to the power of 3. So that's 3 plus I plus 3I plus I squared. So that's how that works. 3 plus I plus 3I plus I squared. So it's 1 times that and I times that. So that's the way it all works. Now, however, I squared, if we go back to the very beginning, is defined as minus 1. That was the definition of a complex number, and we had that at the beginning. I think we had it on this page here. We said that I squared was minus 1. So we have to use that here now. So now we're left with 3 plus I plus 3I minus 1. And again, we can join those bits up together. The 3 and the minus 1 are real, and the I and the 3I are imaginary, in that they have an imaginary element in I. So the 3 and the minus 1 gives us 2, and the I and the 3I gives us 4I when added. So this is really strange. It doesn't sort of come to us naturally to think about it, but it's saying that if we have that complex number here, 1 plus I, and we have this complex number here, another one beside it, 3 plus I, if this is Z1 and this is Z2, when you multiply them by each other, you get this one here. And we're happy to accept it and believe it, I suppose, but it doesn't necessarily mean a lot to us. That by that gives us this. I mean, why isn't it somewhere else? Why didn't it land somewhere else? How does that adding, we know that 2 and 2 is 4, or 2 and 4 gives us 6. We sort of know that, but multiplication of that by that gives us this. A little bit tricky for the moment, so we'll come back to that. But that is the answer, and that is correct. Now, so when they looked at it, they said, that's 3 plus I by that is that. So this by this gives us this, or this by this gives us this. That's the answer. Now, I'll just give a slight hint. But let's call that Z1, and let's call that theta 1, the angle. And let's call this Z2, and let's call that theta 2. Then let's call this Z3, and let's call this theta 3. Is it possible that there's a link between theta 1, theta 2, and theta 3? Just a call. Okay, then we'll come back to it. So that's multiplication. The next bit is called complex conjugates and division. It's not possible to divide apples and oranges by apples and oranges of different amounts very simply. So there's a trick we use called complex conjugates. So in order to do division, we have to bring in this helper, this complex conjugate, this fixer that does it for us. In chemistry, you might be familiar with the catalyst that comes in, helps start a reaction, and then at the end is still there, but it sort of made it all possible in the first instance. Complex conjugate is a bit like that. It's just a useful pairing that happens to come around and helps us do division. So where a complex number is denoted, Z is equal to A plus BI, the complex conjugate is denoted by Z bar. There's a little line or dash above that. Usually we'd see them on the bottom, an underscore, but it's above it. So that's a symbol in maths for complex numbers that says the complex conjugate, and sometimes written A plus BI like that. And it means that Z bar is A minus BI. So for any number A plus BI, the complex conjugate is A minus BI, which is an interesting idea. And the special characteristics of these complex conjugates, really powerful. They have two really cool special characteristics. One is when you add them together, when you add a number with its complex conjugate, you'll have no imaginary bit left. And also when you multiply one by its twin, its complex conjugate, you get no real bit, no imaginary bit left either. So when added or multiplied by each other, they yield a real number, no imaginary component, which is really cool. And we'll see why that's important in a minute. But let's look at a complex number representation. Here we are again on the Argand diagram. This is the imaginary on Sawalchuk. This is the Reidul, the real, not x and y. And this is the point 3 plus 4i, 3 out and 4 up. And its twin is down here. It's, for all the world, like you're looking into a mirror. You're here on this side looking in, and in the back of the mirror you can see the EVA or the image, or the, you know, the other representation behind. Now, it doesn't just work for this one. This is a complex number as well in its own right. And when this looks into the mirror, it sees this. So a complex number doesn't have to be in this quadrant. It can be here or there or anywhere. But if it is, it always has a mirror image. So let's take this one here, this complex number minus 1 minus I. Its twin is up here. So if this is Z2, if Z2 is minus 1 minus I, Z2 bar is minus 1 plus I. Still the same minus going back, but plus instead of minus. So it's exactly similar to the process of reflection of points in the real axis. So there's the real axis and the image, and that's your complex conjugate. And they go around in pairs, unlocking various things. So let's look now at adding complex numbers together and complex conjugates together. Here we've got a complex conjugate 1 plus 2. We've got a complex number 1 plus 2i. So let's call that Z1. Its twin is 1 minus 2i, or Z bar 1 bar is that. So this is 1 out, 2 up. This is 1 out, 2 down. And if you add the two together and you went 1 out, 2 up, 1 out, 2 down, you'd find yourself back here. So 1 plus 2i, 1 minus 2i would be 2 plus naught I. So an apple and 2 oranges, and an apple and owing 2 oranges, you'd keep your 2 apples and you'd have no oranges left. So that's what that is. So that's the step. 1 out and up, 2 up, 1 out, 2 down. So, and you could have started 1 out, 2 down and gone back up this way if you wanted. Okay, but you'd always end up there. So that's what adding complex conjugates do. Multiplying complex conjugates, also pretty interesting. Here we've got 1 plus 2i, 1 minus 2i, and we end up at here. So this number by this number gives us this. Wow, how did that come about? Well, let's see if we can do that and see if the maths are right for that and see how we do that. 1 plus 2i by 1 minus 2i. So 1 plus 2i by 1 minus 2i. Let's do the FOIL method. 1 by 1 is 1. Outside minus 2i. Inside plus 2i. And then 2 by 2 is 4. 2 by minus 2 is minus 4. I by I is I squared. Now, the 2i and the minus 2i cancel. And I'm left with 1 minus 4i squared. But the I squared is really minus 1. And 4 times minus 1 would be 1 minus, well, that would be plus 4, which would be 5. And there'd be no I here, so 5 plus naught I. 5 plus naught I. So this number here, multiplied by its complex conjugate, ends up here. Or this number multiplied by its complex conjugate ends up there. The interesting thing is that we have no imaginary part left. And it does the sums that way, so it's done. Now, why do we get these complex conjugates around? We were able to multiply before then. We're now doing division. So here we've got a situation where we say division. We're going to divide 1 plus 8i by 2 plus 3i. And that's not trivial. That's tricky enough because we've got the two things on the bottom. So this is a technique, it's a trick, and we say we're going to multiply both sides by the complex conjugate to see if that helps. So we're going to go multiply above the line and below the line by the same thing. But we're interested in the complex conjugate of the one on the bottom. So 2 minus 3i by 2 minus 3i. If I multiply something by 4 over 4, it's like multiplying it by 1, leaving it alone. So I'm going to multiply the top bit by this and the bottom bit by this. So 1 plus 8i by the top bit, 2 plus 3i by the bottom bit. So really, if I could ask you to give this a try, and maybe you might start by doing the top bit, which is 1 plus 8i by 2 minus 3i. That's one sum to do. And then when you finish that one, do 2 plus 3i by 2 minus 3i. And see what answers you get. That's the one on the top and that's the one on the bottom. So give that a go for a minute and we'll just see, just get your multiplication of complex numbers underway. Okay, let me give the top line a go. So basically what I want is 1 plus 8 into 2 minus 3i. 1 plus 8i into 2 minus 3i. I'm going to do the first parts first, that's 2. 1 by minus 3i is minus 3i. 8i by 2 is plus 16i. 8 by 3 is 24. 8 by minus 3 is minus 24. I by I is I squared. So I'm going to get 2 minus 3i plus 16i. And the I squared is really minus 1. And minus 1 by minus would make that a plus. So I now have two real parts, the 2 and the 24. So I'm going to make that a 26. And the 3i and the 16i are the same type things. There's minus 3 and 16, so that's a total of 13i. So that's what I got for the top line, 26 plus 13i. And I think if I do the sums on this, and I go through it, 26 plus 13i is what I got for the top. Now, what about the bit on the bottom? What was the other bit? Well, the bit on the bottom was 2 plus 3i by 2 minus 3i. So let's multiply that out. 2 plus 3i by 2 minus 3i. Now remember, this is the bottom number and its complex conjugate. So it really should end up as just a real number. So let's see, 2 by 2 is 4. 2 by minus 3 is minus 6i. 2 by plus 3 is plus 6i. 3 by 3 is minus 9 because there was a minus. And I by I is I squared. Now, luckily, the minus 6i and the 6i, they cancel. So we're left with 0i. The 4 and the 9i squared, well, that I squared is really minus 1. So it's 4 minus 9 times minus 1 plus 0i. But 9 by minus is minus, so that's minus by minus is plus. So that turns out to be 13 plus 0i, or just 13. So again, if I look through the notes here, I can see that what I got on the bottom was 13 on the bottom and 26 plus 13i on the top. 13 goes into 26 twice and 13 goes into 13i once. So the answer I got was 2 plus I. And that's not bad. It looks like a number I can plot on the Argand diagram anyway, so I've got the answer. So effectively, if I divide 1 plus 8i, this number, by 2 plus 3i, using the trick of the complex conjugate, I end up here. So this divided by this gives us this. Again, it's sort of strange. A number somewhere out there divided by a number somewhere out there gives us a number somewhere out there. But if we look at it and we consider this angle here of theta 1 for Z1, and this number here, theta 2 for Z2, and this number here, theta 3 for our answer for Z3, what we can see is when you divide this number by this number, actually the angle that was big is reduced by this to give us this. And that's actually what's happening. We can see actually, and it's an observation, that theta 1 minus theta 2 turns out to be exactly theta 3. And that's really interesting. And if we go back to our multiplication, way back, and multiply this number by this number, theta 1 plus theta 2 gives us theta 3. So the way it works is that when you're multiplying complex numbers, you add the angles of their line to 0 plus 0. When you're dividing, you subtract the angles. Or when you're multiplying, you rotate anti-clockwise. If you're dividing, you rotate clockwise, which is sort of nice. It's a nice way of doing it. So these are just some observations that happens when you look at complex numbers in that way. They said when you multiply complex numbers together, where Z3 is Z1 times Z2, the angle of the product is given by the sum of the other angles. And the angles are those made by the complex number, the origin, and the real axis. So if you have a complex number, for example, here, its angle is the angle it makes with the real axis, like that angle there, theta 1, let's say. And if you think about it, this is a slide from when we were doing complex conjugates. The twin is on the other side, and you'd sort of expect that angle to be the same because whatever height it is, it's whatever height. So that'll be minus theta 1, really. It's just a different, same size. And if you multiply one by the other, you're multiplying it this way a bit, but it's already on the bottom. So all of that angle is made up, and the answer ends up here. So if this was minus 60 degrees and that was plus 60 degrees, minus 60 plus 60 would make it exactly on the horizontal, on the real line. So the angles would actually cancel in that way. So that's what and that's why it ends up, when you multiply the twins or the complex conjugates together, you end up on the real line. So that was a nice observation that they found. Another observation was when dividing complex numbers, where Z3 is Z1 divided by Z2, the angle of the product is given by subtracting the angles. So the theta 3 is one minus the other, and the angles are made by the same way with the real axis. This was one to do with moduli. When multiplying complex numbers together, Z3 is Z1 times Z2, the size, the absolute value, the length of the complex number from 0 plus 0y, its distance, is equal to the product of the other two numbers. So that's interesting. So if they're big, the answer will be very far away from 0 plus 0y, if they're far away already. And the same, when you're dividing complex numbers Z1 over Z2, the actual physical distance of the third one is the physical distance of the first one divided by the physical distance of the second one. And in a way, that's very comforting in a way, because if you imagine, say, real numbers, if that was the number 2 and this was the number 4, 2 times 4 would be, well, let's say it's 8. So 2 times 4 is 8. Or 2 plus 0i times 4 plus 0i is 8 plus 0i. So it works. And all we're saying that if you've got a point there, like this one, and you've got another one here, that one, you take the first angle here, the second angle here, and join those two together to get the third angle. And if this is a certain length and this is a certain length, the answer will be a lot longer length to get it. So that's how you do the complex numbers. So that's an interesting observation. So if we look back at our sums, there's multiplication of 3 plus I by 1 plus 2i. That's the angle, the other angle, and the angles added together. So the answer turns out to be the sum of the angles, and the lengths turn out to be the product of the lengths. So that's how it works in multiplication. So that's how it would work. And in division, if we started with 1 plus 7i and divided by 1 plus 2i, we'd be rotating back this way to end up there. How would we do those calculations? Well, we could do it in lots of ways. We could rely on different parts of the course, but let's just take 3 plus I and 1 plus 2i for the moment. And let's call this 1, 2, 3, and let's call that 1, 2, 3. And let's say the first one is 3 plus I. So that's 1 point, and the other is 1 plus 2i, and that's the other. So this is Z1, and this is Z2. How would we find out the length of Z1? And how would we find out the angle? How would we find out theta 1? And how would we find out this length of Z1? Well, if it was a different topic on the course, like trigonometry, we'd say, that's a right angle triangle. I know this is real. I know this is imaginary, but it's working exactly the same way as X and Y. That's 90 degrees. If that's 3 and that's 1, 3 plus 1, we should be able to get the length from Pythagoras. 3 squared plus 1 squared would make that the square root of 10. How do we find the angle there? Well, we don't know, but we know that that length is 1. We also know that that side is opposite that angle. So this must be the opposite. If that's a right angle triangle, the one facing the right angle must be the hypotenuse. So that's the tevagon, that's the orchorok. This must then, the only one left must be the adjacent or the congruent. So you've got the adjacent, the opposite, and the hypotenuse. How can we find out that angle? Well, we know that the opposite is 1 unit of length. And we know that the hypotenuse is the square root of 10. Or we also know that the adjacent is 3. We can pick any one of those to solve it. So for example, let's take tan of theta 1 is opposite over adjacent, or orchorok or congruent. So we get tan of theta is 1 over 3. That over that. What's theta? Inverse tan 1 over 3. And whatever that angle turns out to be is an inverse tan, we can find it out. So we have that theta. Okay, so we can find the theta 1, we can find the length. If we can do it once, we can do it twice. So if we look at Z2, we can say Z2 is 1 out and 2 up. So that's 2 and that's 1. That's going to be its own theta 2, which we can find in exactly the same way. That's going to be its own length, which we can find out through Pythagoras in exactly the same way. 1 squared plus 2 squared would be, that's the square root of 5. So now we know that Z1 is, whatever it is, in terms of modulus, is the square root of 10. Z2 must be the square root of 5. So what's Z3? One thing times the other. And the square root of 10 by the square root of 5 happens to be the square root of 50. Okay, and that's the way that works. And the same for the angle. We could find that angle, find the other angle, and add them up. So that's how all that will be done. So that's complex numbers. But before we go on complex numbers from this section, I want to just show you something that's really, really, really important about complex numbers, because you have been using them all the time. You've used them today several times. You use them all the time. You share images with your friends online. You look at various photographs that you've taken. And let's just imagine what's happening. What I said was, if you've got a complex number here, any complex number here, and you multiply it by another complex number, Z1, Z2, you end up rotating. So you rotate the point around. The further you are from zero, the bigger the thing gets. But just imagine if you were just a perfect amount from zero. You weren't too far away, you were just right. Let's imagine you were just 1 unit from zero. And let's imagine that that's the point 1, 0, I. 1 plus 0, I. Let's imagine that this one here is I, it's 0 plus I. So that's the point 0 plus I, and that's 1 plus I. So that's Z1, and that's Z2. If I multiply 1 by I end up with I. In other words, anytime I multiply something by this, I'm actually multiplying something by something that has an angle of 90. So if I multiply 1 by I, this point that was here somehow ends up there. It rotates through 90 degrees. If I were to multiply it again and get I by I, I'd get I squared, which would be minus 1 and no I, and I'd end up here. Minus 1 plus 0 I. If I did it again, minus 1 times I, I'd end up at minus I. I'd end up down here and here. Now, not a very good circle, but you get the idea. What's happening is every time I multiply by I, I'm actually rotating the image. Now, I won't show you what's on my phone, but every time you turn your phone from this way to this way, you have a picture that you'd prefer to show this way or this way, and you see your friends or whatever you want to show your background in that light. What you're doing is your phone is actually multiplying by I. It's causing everything to rotate by 90 degrees. That's exactly what's happening. So that's the way it works perfectly. So I don't know if I can do that now, but if I come into the camera, I don't know if I'd necessarily try that. But basically, in terms of the camera, I could also flip the camera around through 90 degrees. I don't think I'll do that. It'll probably disorient me more than anybody else. But that's the way it works. So how often have you used complex numbers today? How many times did you turn your phone from this to this, from landscape to portrait and back again to look at various things? And that would not be possible without the two-dimensional image flipping absolutely 90 degrees every time. That standard rotation of 90 degrees and again and again and again. So that's what complex numbers are for. That's how you can work out all that. And that's the complex numbers. Now, we're sort of done with complex numbers in a way, in the basic stuff, but sometimes they try to throw in complex numbers with another part of your course. So what I've done here is I picked a few areas of the course where they could use complex numbers with another part of your course. Here it is with arithmetic and algebraic equations. You've heard of BOMDAS, brackets, order, multiplication, divisions, addition, and subtraction, that order of which you do first, or the Americans call it PEMDAS. Please excuse my dear Aunt Sally. They do the parentheses before the others, etc. But here's a reasonably long sentence in mathematical terms that they want you to simplify. Simplify 3 plus I into all of these. And all we have to do is to remember, what is the order? Well, we do inside the brackets first. Inside the brackets, it looks like we have a power, I squared. So let's do that first. So 3 plus I times 3 by 2I plus I minus 1. The I squared becomes minus 1. We still have the same stuff, but that's 3 by 2I. That's multiplication within brackets. So we'll do that first. So 3 by 2I is 6I. So now we have 3 plus I times this. 6I plus I inside the bracket, they're the same type of thing. They're both imaginary, so we can add them up to get 7I minus 1. So 3 plus I. And there's nothing more we can do here. We can't add the i's and the 1's there. That's not going to get any simpler. Now, we might have said minus 1 plus 7I, but that's as much as we can do. Let's multiply in now by the I. So I by 7I will be 7I squared, and I by minus 1 will be minus I. So there's the 7I squared and the minus I. Now we're left with the I squared. That's a power. So we're going to simplify that down to minus 1 times. So that becomes a minus. So 3 minus 7 minus I. 3 and 7 are the same type of thing. They're both real. So 3 minus 7 is minus 4 and minus I. So the answer, or the simplification of all of that, is that basically instead of that being as long-winded as that, it's just the point minus 4 minus I. So that's one. Now, I said this before about complex numbers, and it says if two complex numbers are the same, if they are to be the same, if u and v are the same point, or they'd be the same, well then the real parts here have to be the same and the imaginary parts have to be the same. So if John and Sive have the same numbers of apples and oranges, the only way they can have identical sort of values is that if they've got the same number of apples and the same number of oranges. So they might have 3 apples each and then 7 oranges each or whatever. They can't compensate. They have to have exactly the same for the apple score and also for the orange score. So here's a question now in complex numbers that you might say, we didn't do anything like this. But what they're doing is they're using the algebraic part of your course and seeing how you do it. They say solve this. S plus ti is 1 plus 3i squared. And you say, okay, never seen anything like this before. But it's possible, and it's on the syllabus, and they can ask. So let's see if we can go anywhere. 1 plus 3i squared, I think we could simplify. 1 plus 3i by 1 plus 3i. And that's multiplication of complex numbers. I know how to do that. So let's just work it out. So 1 plus 3i is 1 by 1 is 1. 1 plus 3i again. 3i the other way back. And 3i by 3i is 9. I squared. The I becomes minus 1, etc. So that's it there. Or the 3i and the 3i become 6i. And the I squared is minus 1. So I end up with this. The 1 and the minus 9 are real, so 1 minus 9 is minus 8. So I'm now left with this. I haven't answered the question, but I've gone somewhere. I was asked to solve s plus ti as this, and now I've said s plus ti is this. But s is a real value, and t is a real value. So it's saying the real part of the left-hand side must equal the real part of the right-hand side. The imaginary part must equal the imaginary part. So if the real part is s, the real part here is minus 8. So s must be minus 8. And if ti is 6i, well, the i's cancel, t must be 6. So s is minus 8 and t is 6. So even though we mightn't have thought of being able to do that, that's all they were asking us to do. That's example 1 in algebra. Here's another question that would put you off maybe, because you'd say there's a lot going on here. K into w plus w bar is 20, where w is equal to 2 plus 5i. You say, this is very complicated. Hold on a sec. But remember, it's so important to remember what these little symbols are on the top. Just as we know what an apostrophe is, or an exclamation mark, or a full stop is, or a capital letter, just as important in maths. So this bar means the complex conjugate. It's the mirror image. So it's saying that W is 2 plus 5i. Well, W bar must be 2 minus 5i. The opposite in the mirror. If that was minus, this would be plus, that's plus, this must be minus. And we're now saying K into W plus W bar. Well, what's W plus W bar? Let's add them up. 2 and 2 is 4, and 5i and minus 5i cancel. And that makes sense, because remember that when you add a number to its complex conjugate, you must get a real number. So really, W plus W bar is just 4. So here we go. Let's go through it again. W is 2 plus 5i. W bar is 2 minus 5i. We add them up. We get equal to 4. Now let's look at what we have. We have K times 4 is 20. So K times 4 is 20. K multiplied by 4 is 20. What's K? Well, that's a bit easier. K times 4 is 20 is like 4 times K is 20. And then you say, how do I get rid of a multiply? Well, I divide, and I get K is equal to 5. So again, we probably wouldn't have expected to get such a straightforward answer from something that looked as complicated as that. But we gave it a go. We plugged in. We would have picked up the mark for spotting it was the complex conjugate, another mark for writing it down, adding them up, working it through, and it's done. So a few more before we finish. Example 2, a little bit more complicated now, a little bit less likely, but it is possible. It's on the syllabus, but they're getting a little bit trickier now and less likely. But just let's have the skills. Here they're saying x into 1 plus 3i plus y into 2 minus i is equal to 2 plus 3i, or plus 2 plus 3i is 7 plus 4i. So that is a long question. But if it's a long question, they might give you 50 marks for it rather than 25. So let's solve that. So again, the important thing is remember that the ones are the apples and the i's are the oranges. So just keep all the real bits together and all the imaginary bits together. So we say x by 1 is x, 3i, x, and all that. But let's get the real bits together. So that's a real number. The 2 is real, that 2 is real, and that is real. And we do the i's later. But on the real bit, we've got x by 1 is x, y by 2 is 2y, plus 2 equals 7. We could take the 2 over to the other side, and we get x plus 2y equals 5. Well, 7 minus 2, we could cancel it and all that. So let's imagine that's one equation. Now let's look at the imaginary part. 3i times x will be 3xi. Minus I by y will be minus yi. 3i will be 3i equals 4i. Now let's get rid of all the i's because we don't need them. Okay? And we get 3x minus y plus 3 is 4. I don't like the 3 on this side. I'm going to bring it over to the other side. 3x minus y is 1. So what I've got is I've got two sets of simultaneous equations, okay, at the same time. X plus 2y is 5, 3x minus y is 1. Nothing to do with complex numbers anymore. This is just the solution of 2 Courtomodi. That's all, 2 equations. So effectively what we've done is, looking at this slide here, we brought all the real bits together and all the imaginary bits together. We grouped them all together and we ended up with 3x minus y is 1, 2x, x plus 2y is 5. 2 simultaneous equations. Okay? How do we solve those? In the standard way in algebra. So Let's look at other things in polynomials. We would have seen this before. But just to let you, just before I start, I'll talk about complex numbers for a minute. There's a famous mathematician called Rowan Hamilton, and he really liked these I-squareds and all of these, not only in 2 dimensions, but in 3 dimensions and many dimensions. He thought about them not just in 2 and 3 and all these imaginary numbers. And around 1880, he was out for a walk in Dublin along the canal with his wife, and it just struck him. He had been working on a problem for a long time, and it was really, it came to him how elegant the whole thing was about the rotations and all of that he stopped the chat and he had to write it down. So he chiseled the answer into the bridge wall along the canal. And every year people walk to that bridge just to honor him and all the things that are done. But we certainly wouldn't have the iPhone turning around as it does, not only in 2D, but in 3D for all the games and all the other virtual realities and augmented realities that we enjoy, were it not for an Irish mathematician, Rowan Hamilton. So let's look at complex numbers and roots of polynomials. We've seen these quadratic functions that swing and come down and cross the x-axis. In functions and graphs, we would have seen one of those, find the roots, find out where it intersects, etc. Sometimes it can be nice and fine, and it can just about touch the line, where the roots are actually the same. The roots of that equation there are the same. I think it's x minus 3 and x minus 3. So the 2 points come together. But above this, they don't meet at all. And many years ago, when you did the minus b plus or minus the square root of b squared minus 4ac over 2a, usually, at least for the junior certificate, this number here was always positive. You always got the square root of something that was positive. But you can also get the square root of something that's negative. And if you do, it's just the square root of minus 1 is just I. The square root of minus 4 is really the square root of 4 times I, which is 2I. Or the square root of 36I minus 36 is minus 6I. So we can solve them now, whereas in the junior cert we would have said it's not working out. My calculator is showing an error. So this one here, while it doesn't have real roots, it will have complex roots. So complex roots, an example, here's the roots of the equation z squared minus 6z plus 12. Find the actual roots. Well, it's exactly the same as before, ax squared plus bx plus c, but I'm using az squared plus bz plus c. So that's the function, z squared minus 6z plus 12. I write down a, the first number is 1, b is minus 6, and c is 12. And here is the formula. I now plug in my answers on the next page. I've copied these across. I'm in the zone. I've taken concentration. I'm writing them down. And I rewrite out the equation, minus b squared, and I start copying them in. But on this equation, I get the square root of minus 3. So that's tricky. So what I do is I call that the square root of 3 times I beside it. And they're the roots. So the roots of that equation are 3 plus or minus the square root of 3i. So they will not work on your standard real number line. I won't get a number like 2, 3, or 4, but I'll get a number like this. And just imagine, let's go back for a moment. Just imagine how boring in a way, or how limiting in a way, real numbers are. 1, 2, 3, 17, minus 11. You know, you're walking along here on the real number line. 0, 1, 2, 3. It's all interesting. You might say hello to pi along the way. 4, 5, 6. The square root of something if you want. Very nice and all that. You might go minus. But it's really limiting, up and down your whole life, going up and down this straight line. Never going north or south, just going east or west. And then complex numbers come along and say, hey, you can step off this line, you can go up here, or you can go over here, or here, or here, or here. And when you multiply this by this, you can end up way over here somewhere through rotations. So that's really what's happening here in these complex numbers. The roots of that equation are 3 plus root 3i. So it's somewhere maybe up here. And 3 minus root 3i. So a root there and a root there. And again, the root with its complex number parent, the twin. So that's what that is. So let's look at the complex numbers. We say we get the roots 3 plus 3i, and it says put the answer back in. So I'm going to say, what is the value when I put in f of that? You might remember much earlier when we solved a quadratic, or we solved a simple equation, something like this, where there were, I think it was at 4 and at minus 2 or something it crossed. We said when we put in f of 4, we ended up with 0. When we put in f of minus 2, we ended up with 0. Well, with complex numbers, if that's the quadratic, or if that's the quadratic complex equation, and we plug in the root, which we think is 3 plus root 3i, and everywhere we see z, we put in 3 plus root 3i, we get f of this is 3 plus root 3i squared minus 6 times this plus this. So we multiply that out, multiply that in, multiply that, get them all together. See what happens? 0 plus 0i. Just as we would have got for the real ones, would have been 0. It's showing it is a root. If there are two roots, one has to be the complex number conjugate of the other. So if one is that, the other. Then the two factors are, so if z equals 3 plus root 3i, then z minus 3 minus root 3i must equal 0. Because that's just moving that to the other side. And if that equals 0, this must be a factor, whereas this must be a root. So exactly the same as we started in real numbers and real equations, it applies exactly the same for complex numbers. So multiplying the two factors together, this is the one factor by the second factor. We end up multiplying them all in, quite complicated all the way along. Z squared minus 6z plus 12. Exactly the same equation that we started out with at the start. When the roots of a quadratic equation are known, the quadratic equation can be expressed as this. This is a trick that some people do in other parts of the course. It's z squared minus the sum of the roots and the product of the roots. So the sum of the roots, if that's a root, the other one is the complex conjugate. So that becomes 6. The product of the root is the 3 plus root 3i by 3 minus root 3i. Again, you can multiply all of those things out and get the answer there, 12. And what do we get? The function is z squared minus 6z plus 12. Exactly the same again. So you can use the roots in so many different ways. Once you know them, it's done. And the final example of this in the notes, and I'm just going to do some show you how simple some of the exam questions have been and how straightforward they've been. But this is as complicated as the syllabus allows it to get. It could be asked, more likely to be asked, not in complex numbers, but in ordinary equations. It's saying, given that this number here, z1, 1 plus 3i, is a root of the cubic equation this, find the other two roots. So it's given you a cubic equation, complex number, and given you one of the roots. Imagine if this was not in complex numbers. They would have said something like this. X equals 2 is a root of the cubic equation x cubed minus 2x squared minus 6 plus 7 equals 0. Find the other two. Here they're saying, this is a root of this. Find the other two. But if this is a root its complex conjugate has to be there as well. So an other root has to be Z2 is 1 minus 3i. So if they tell you one, you know a second one. So automatically you're nearly there. So you know one root, you know the other root. If you know one root, you know that Z1 minus 1 minus 3i equals 0 by just bringing it to the other side is a factor. You know that Z2 minus 1 plus 3i is another factor. So you know two of the factors. So now we can say this must be a factor and this must be a factor. If they're factors, you can multiply them together. Just like if x equals 2 is a factor and x plus 4 is a factor, you could multiply those together. So I'm going to multiply those together and I get all of this. So I now know that z squared minus 2z plus 10 equals 0 is a factor. So all I'm looking for is the last one. So another way of doing that was a different approach, is I could have used the sum of the roots and the product of the roots, given that I knew that this was the first root and this was the second root. The sum of them was just the 1 and 1. The product was that whatever would turn out to be, I think, 10. So again, I get z squared minus 2z plus 10, z squared minus 2z plus 10. It's just an alternative approach to exactly the same. So very last, if I now know that this is a root, and I know that this is the cubic equation, I can divide in. Just as I would if this was a real question, like x squared plus 6x plus 9 divided into a big cubic thing. So I'm going to do it. How often does z squared go into z cubed? Z. So z times all of this gives me this. Z cubed from this gives me nothing. I add those up. I'm left with this when I do the subtraction. How often does z squared go into minus z squared? Just minus once. I do that in and look at it. It's neat and tidy. So effectively dividing in just as I would for the real numbers, I get z minus 1 is the other root. Z minus 1 is a root. Z equals 1 is a factor. 1 plus 0i is the other, root. So z minus 1 is a factor. That's the root. That's the position. So the three roots are there for the first one they gave us, the second one, which we knew, was the complex conjugate, and the third one, the one we found. So that is the entirety of the syllabus they're allowed to ask. They haven't asked on the cubic yet. It's unlikely that they would, but it's nice to know that it's there. They could certainly ask it if it wasn't complex numbers. So it's just exactly the same calculations. So with that, I'm just going to just stop there for a second, and I'm going to pull up some of the complex numbers questions that we've seen in the last while, and just to show you how straightforward they are, and just to say we'll certainly pick up all the marks on that. So just slán tamil. So complex numbers, just a few questions, and I'll just pull them out here. They're pretty straightforward. I'll take the last 3 years, and the first one was something like z1 is equal to 2 plus I. If z1 is 2 plus I, find z2, where z2 is 2 times z1. So in other words, multiply that by 2. So if you have 2 apples and an orange, what would happen if you had double that? Well, you'd have 4 apples and 2 oranges. So that won't strain you. The next one then is, what's z1 bar? What's the complex conjugate? Now, as long as you know what that symbol means, it's 2 minus I. And then they ask, is this modulus here, is this equal or not? Is the length of Z2 equal to the length of these two together? Well, Z2 is whatever that would have been, 4 plus 2I. What's the length? The length is the distance. It's the Pythagoras thing. So if it was 4 out and 2 up, we'd say 4 squared, 2 squared, 4 squared, 2 squared, square root it. So I think that's 16 plus 4 is 20. So is the square root of 20 equal to Z1 plus Z1 bar. Well, Z1 is 2 plus I. Z1 bar is 2 minus I. Z1 plus Z1 bar would be 2 plus I plus 2 minus I is 4. Is the square root of 20 equal to 4? I don't think so. I think the square root of 16 is 4, so that's not right. So the answer was no. And that was it. That was 25 marks or whatever. And you do it in a minute or 2 or 3 and be sure of it in 5. The next question was like this. And they said, here is the Argand diagram. And this is a point on it. What is that point? What is it in terms of A plus BI? What is the A value and what is the B value? And it's 3 plus 4I. So the answer was 3 and 4. What you had to do there was remember that the real bit was first, just like the X, and the imaginary bit was here, and that was 3 plus 4I. The question went on and said, Z1 is now 3 plus 4I. Z2 is equal to minus 1 plus 2I. Find Z3, which is Z1 over Z2. If you're dividing by Z2, we'll have to get the complex conjugate. So the question was 3 plus 4I divided by minus 1 plus 2I. You know you can't do that easily. So the trick was to bring in the, I suppose, the thing that sorted it out, the minus 2 minus 2I, minus 1 minus 2I, that's multiplied there. And you know that when you multiply this by this, it would be a real number because that's what it does. That's why you chose that. It sort of magicked it away. This is going to be some number that you divide by a real number. And that was that question done. And that was it. The last question was you're given a number, which was Z1 was equal to some value, let's say 3 plus 4I. Z2 was equal to 2 plus 7I. And the question was, is Z1 times Z2 times cosine theta equal to AB plus, AC plus BD? Sorry, that was A plus BI and C plus DI. They could have done it with numbers. They could have said, is it equal to, you know, whatever that is. Okay? So, how would you do that? Is this true? That was the question. So let's look at it here. They're saying, here is a complex number, A plus BI, Z1. Here is a complex number, Z2. C plus DI. And the question was, is Z1 times Z2 times cosine theta, which is this angle here, equal to AC plus BD? Now, how would we do that? Well, the first thing we've got to do is to find out what the modulus of Z1 is. How do we find the length of Z1? So if we know that it's A plus BI, so I'll just write it on that. And let's say I think it's 4 out and 1 up. So 1 up and 4 out. A plus BI. What is the length of that? Well, that would be 4 squared plus 1 squared because it's Pythagoras. If this was A and this was B, that would be A squared plus B squared. So the modulus of Z1 is A squared plus B squared square rooted. It's the length of it. It's not the square of it. What's the modulus of c plus di? Well, it's pretty much the same. It's the c and the d. So it's c squared plus d squared, because you go out c and up d. So c squared and d squared. So that's the first two bits. But how do we get this angle here? Even not to mention the cos of it. How do we get that angle? Well, let's imagine that we have something here like this. Just get a better pen for a moment. So that's the first one. And we're looking for this one. I think that was, let's say that's 4, 2 or 2, 2, 4, I think I called it. How do I find that angle there? Well, I can certainly get this angle here, theta 1, because if that's 4 and that's 1, I know that, I can find the tan of that, because the tan, that's the opposite over adjacent, or coric or congruent. Tan theta 1 is equal to 1 over 4. Theta 1 is inverse tan 1 over 4. What about this fella here? Well, I can't find the angle in the middle very easily, but I can certainly find this angle, because this angle is just simply 2 out and 4 up. So 2 out and 4 up, can find that angle handy enough. It's 2 and it's 4. It's a right angle triangle. So 4 over 2 is the tan. So theta 2 is, well, I don't know, but tan theta 2 is 4 over 2, because the opposite for the theta is there. That's the opposite. So theta 2 is inverse tan 4 over 2. Theta 2 is inverse tan 4 over 2. What's the angle in the middle? This one minus the other one. So theta 3, the angle in the middle, is theta 2, the bigger one, minus theta 1. And that's the angle. So the question was, can I actually solve this? I think I can. I think I can find the two z's, I can find the theta, I can find the cos theta, and I can see, is it equal to this? And if it is, it is. And if it's not, it's not. Doesn't matter. You were just asked to find out whether or not it was. So I'll just finish there for a second and say stop share, and back to me. And I'd say thank you again. I'd like to thank John and Rob, who've been with me all day, and Sinead, our school's liaison, and all the people who've helped allow us run it. We were hoping that we could invite you into the campus, but we're delighted that we invited you in online. Take care, look after yourselves, look after your families, and you're getting through this. And Ganari Gal lives in Scrutha, and enjoy the summer when you get it, and enjoy college when you get it. Slán, Banacht.